In section 5.5, we're going to start to talk about the topic of surface integrals. And we'll begin by looking at this motivation. So consider a curved lamina, maybe like this Pringle type shape that I have over here on the side. And let's say that that can be modeled by then some sort of smooth surface that we'll call sigma. Now, what we're going to imagine here is that we're going to have a function of three variables, but this function doesn't create this 3D surface. What it does instead is it maybe measures the area density at any point that is on that particular surface. So, if you were to imagine a point on this particular surface, maybe like right here, my function f would actually be measuring the density at that particular given point. So what we want to try to do is to answer the question, is it possible that we could determine the mass of this lamina, the mass of this surface? Well, in order to do this, we'll start with a pretty common technique. I'll say here that we can begin by partitioning sigma into n patches. And you kind of can see that here in this second picture, that I've kind of chopped up this lamina and I've kind of put these different lines across it to kind of divide it up in these different like rectangular or pseudo-rectangular-ish regions. And so what we're going to do is we're going to go ahead and zoom in on one of those regions. And so we'll say, consider the kth patch. And we're going to go ahead and choose a representative point. We'll call this P sub k, so it's a point that belongs on the kth patch, and it's going to have special coordinates. It'll have a special x coordinate, it'll have a special y coordinate, and of course it'll have a special z coordinate. Again, this is just to indicate that somewhere on this patch we're going to be selecting this P sub k point that I have shown kind of down here. So we'll select this special representative point for this patch. And once I have that particular point, I could start to see some things. First off, I could say, well, if we let delta s with subscript k represent the surface area of this patch, and we let delta m sub k represent the mass of this particular patch, then we should be able to go ahead and define the following. We should be able to say then that definitely the mass of this particular little patch should be given by the density multiplied by that surface area. Now, we would need to have the density for every point, and so we won't be able to actually find that, but we can use this density at this particular point as kind of a rough approximation. And so, again, instead of saying that we're going to be able to define exactly the mass, we'll say that the mass can be roughly equal to the function evaluated at our xk star, yk star, zk star, and that multiplied by our delta s sub k. So again, this would be kind of like a representative mass of that particular patch. Again, what we've done is we've selected a representative density. The density might change at different points, but if we use this as a representative point, and then we multiply that by the total surface area, we'll get ourselves an approximation of the mass. But then we could imagine repeating this process for all the different patches that are in the figure. So I can say that we estimate that capital M, say the overall mass, would be the same as just kind of going along and adding up all of the different smaller masses that we get from each of these different approximations. Again, obtained by taking my special point and plugging it into my function to measure the density, multiplying that by the given surface area that I'm working with, and starting at, say, patch number 1 and going to patch number n, based on how many patches there are. And so we would expect that as we begin to let n increase, maybe as n continues to get larger and larger and larger, and we have more and more and more patches on here, they all get smaller, we would expect that our approximation would eventually approach the correct value. So then I can say that therefore we expect that m could be defined exactly as the limit as n, the number of patches, goes off to infinity. But of course, the moment that we do this, we might recognize that we're creating something very, very familiar. What we have here is, again, a function with a special point plugged in and this delta sk. But what that gives us ultimately is, well, this is a double integral. Notice that although I don't have two summations here, my n is kind of standing for all the patches that move in, of course, two directions, left to right and for this front to back. So I would kind of have to be working with a double integral that works over this particular surface of sigma, and I'm measuring the density at every single possible point multiplied by the surface area. So this right here is a way that I could actually go ahead and compute the mass. And so we have this in our definition down below. Assuming that f is continuous, the surface integral of f over this particular surface, oops, this should say sigma here, over the surface sigma is given by this integral. Now, this, of course, is, again, one of these classic instances that we'll see throughout Chapter 5, and we've already seen a little bit back in the previous chapter, that oftentimes while we can create an integral that can go ahead and model something that we're interested in finding, like the mass of our starting lamina, it's difficult to imagine how we would compute this, because even if I have the function, what am I going to use to understand the bounds here on my double integral, and what does it really mean to have this ds? So instead what we'll do is we'll say, how about we let our surface be modeled by a parametric function. So suppose that I have a parameterization of the surface sigma given by this r of uv. Now back in section 4.4, we saw that if I ever had a patch, that we could approximate the area of that patch by using, you might remember, the magnitude of the cross product. This gave us an area of a parallelogram that would roughly be in the shape of this patch up here. So if my delta S sub k can be replaced with this, notice then that I can go ahead and update what's going to be happening in my integral. So my updated definition would say is that assuming that my function's continuous and the surface integral over my surface, again, that should say sigma, my apologies, is going to be able to be, again, the same as what we had it stated as before, but when I make the appropriate change here, I'll be able to see this becomes much easier to compute. Again, what I can do is I can change out my f function, and essentially what I'll have to do is I'll have to put f in terms of my u's and v's that come out of my r function, and then I'll have to go ahead and say that I'll replace this ds with my magnitude of the cross product, dA. But of course, if I'm working dA, then that means that I'm working over a region D that this surface exists above. And so this form is actually surprisingly easier to compute than what we had originally, but it should be noted that this only then works well assuming I have a nice parameterization of the surface. And so we'll see that in all the examples in the upcoming videos, at least for the next several videos, we're going to be dealing specifically with parametrically defined surfaces. So note though one interesting thing. Let's suppose that this function that I had at the beginning was the function just of 1. So this just said 1 ds. Well then actually that would just be an integral that would look like this. It's just be integral ds. And that would actually then, when converted over, look like this, which we might notice is exactly a surface area formula for the surface of sigma. So if my function is a 1, that is, if there's essentially almost a constant density at every single point of 1, then this integral will just compute the surface area. So the nice thing about this is that it means that this isn't really a new formula to memorize. It's an old formula, we just have to understand with this new updated twist.